Um, so I hope my screen is visible. Let me turn my camera off because that'll just make. Okay, thanks, Chris. So let's go over the end of the semester again. So I've updated stuff a little bit. So today we're going to talk about credible intervals. And so I'm going to do some topics that have not been covered on qualifying exams in the past. And I won't test you on it. The test that you'll get on the 30th will be on the information that goes through today. So I'm going to, what I thought about doing is you see chi-square test everywhere. It comes out of an asymptotic analysis that's embedded in understanding the Fisher information for multi-dimensions. So we've learned a lot of that stuff already, so I thought it would be good just to keep going, and we can learn the rest of it. And then if there's a little bit of time, I'll talk about general linear models and how that works, for example, to give you inference for regression in ANOVA. I don't know if I'll have time for that, but we'll see how it goes. Then exam 2 is the 30th, and here's what I'm evolving to is that I will send out a document. Let's say the 30th at 8 in the morning. The beginning of the document will be a statement that you will abide by academic integrity, and you'll send that back to me right away. And then the rest of it will go as a take-home exam, which means, and you'll have a day. So you'll have 8 a.m. and you'll have 24 hours, no matter where on the planet you are. That seems like everybody faces the same sort of times during those 24 hours, and then you upload it and turn it back to me. This means the exam will be, somewhat more difficult than it would have been if it was an in-class exam, but it makes monitoring and proctoring it and so on much less difficult. The other thing that will allow me to do is we've done some interaction with R, that is when you compute a credible interval or prediction interval or so on. I may ask you to do some simple computations in R and upload it to the exam. So you'll do a little bit of R that attaches yourself to the theory, or at least I'm leaving myself open to that. I haven't designed the test yet. So that's what it looks like right now. I hope it doesn't change. I had a long conversation with Zhao Ying about this yesterday, I guess, and I missed some of your office hours. So that's what it seems like we're settling to. If there are any questions about it, let me know. And you'll have to let me know right now. But we'll get to it soon. There's something wrong with the slide. Okay, so yeah, so it'll be open. So yeah, you'll be allowed to look at things. I can't, if it's 24 hours, yeah, you can use notes and a book to that. And then let me see why the slides seem to be in trouble. So let's see if I can upload it. Okay. Okay, see if I can get the slides so that you can see them. That's odd. Okay, let's see if that helped. There they are. Now oh yeah, I added something just a few minutes ago, so there are actually 11 slides. So today's lecture is a little short. And this one had 9, but I thought at the last minute that I would do one more bootstrap just to see how it works. I was curious about how it would work, and so since I was curious, I thought I would just share it with everyone. Okay, so now let's view the So I'm going to do one more bootstrap. Then I'll tell you about credible intervals and their relationship, and then I'll compare approaches, that is the relationship and the interpretation of credible intervals and confidence intervals. They have sort of the same types of differences in interpretation that you saw with the nature of hypothesis testing under the classical and the Bayesian framework. And so we'll modify those kinds of statements at the end. So I'm going to look at what I decided to do is I would look at the Icelandic trios and see what the bootstrap would do to try to estimate the slope. So there are the data. I mean, there's a summary of the data. So you may recall that for each year of life, on average, a child born with parents a year older will have about 2 more mutations. And so that's the mean, and the standard error for the age is 0.1904. So I use that to build a 95% confidence interval, right? So that's 2.1255, and then there's 76 degrees of freedom. I suppressed that part of the output, but it's 78, which is the total number of observations, minus 2, times the standard error, which is 1.904. And I got that the upper limit for the slope was 2.504. And then if I subtract that, I get a lower limit for the slope, and that's 1.746. So it's a symmetric interval with 2.1255 in the middle. Okay, so let's see how it would work with the bootstrap. So I'll create for myself a vector of length 10,000. Then I'm going to pick 78 choices from that sample of size 78, and the way the bootstrap, so the sample size is the same for the bootstrap data set as it is for the genuine data set, and if that's the case and you're going to get some variation, you have to allow replacement. So replace is true, and then I collect the data that comes with that. So the age in the bootstrap is the age for whatever that label is. So I just pull out those labels. So if the labels were 9, 14, 7, 12, then you would see a list of the age went with 9, with the 14th person, the 7th person, the 12th person. The same would be true for the number of mutations. So now I have a new data set of length 78 on bootstrapped Icelanders with their ages and their mutations. So there'll be some repeats. So then I can compute the slope by using the regression model LM of mutations V tilde age V, and the coefficients 2 means I take off the first entry in coefficients is the intercept, and the second one is the slope. So now I have 10,000 slopes. So the mean of the slope was 2.10, which was a little bit less than the mean of the slopes under the which is a little bit less than the slope under the regression model. The standard deviation was 0.23, so that's a little bit bigger. It was 0.1905 under the regression model. And so that means, not surprisingly, we're going to get a little bit bigger confidence interval. So if I stick to the 95% confidence interval, then I'll take the bootstrap slopes, all 10,000 of them, and I'll look at the 2.5 percentile and the 97.5 percentile. And that gives me a slightly wider confidence interval. It goes from 1.655 to 2.553, whereas let's go back with the confidence interval derived from the t-distribution, and the linear regression went from 1.75 to 2.50. It's a little bit wider, right? Okay. So in classical statistics, the estimate for the interval is called a confidence interval, and in Bayesian statistics it's called a credible interval. So remember that when you do Bayesian statistics, both the data and the parameter are random, and after you've collected the data, only the parameter is random. So the interval estimate is a statement about the posterior probability distribution of the parameter theta given the data, x. So I'll write it down there. So So you pick some interval C of X that's based upon the data, and the probability that your parameter lands in that C of X is some number gamma, and that's called a gamma level credible interval. Is that what I write? So in this case, you can absolutely say that the probability that theta is in the credible interval given the data is gamma. So, whoops. Oh, that's a good question. He's saying the bootstraps done on the residuals given in the original model set of the sample. Are the results the same? Yeah, that's a tough question, Nathan. So okay, and so in your case, Nathan, if you do what you said, then you've bought into the slope, right? So I guess you've taken out the uncertainty of the slope of the regression line, and you're putting all the uncertainty in the confidence interval into the bootstrap. So that's an interesting question. We'll try that. I'll try that. I'll send everybody the data set, a way to get to the data set, and we'll try that and see if it does a better job. So that's actually a great question. Okay, so the typical choices, although I'll say a little bit more about that later on in the lecture, is to choose the narrowest interval you can, which involves choosing those values of highest posterior density. Now, there's a fair amount of discussion that you see in different textbooks of what happens in the case that your density is not unimodal. Then you could get a credible interval that's not connected. So it include different values and skip include another set of values if it was bimodal and the confidence interval, or excuse me, the credible interval was of the right size. We're not going to face that here. I'm looking at almost anything that's unimodal. Everything I look at today is unimodal. The other thing is equal size tails, which the probability being below the tail is as likely as being above it. That's a little easier to, we'll see in a minute, it's a little easier to do in R. So that's sort of, or anything is sort of simple. You can just use the posterior distribution of the parameter given the data, and then just announce its distribution and see where it comes from. Okay, so to look at it for independent flips of a biased coin with a prior distribution that's from the beta family, so this is a situation that we've seen in the past, then the prior is some constant, and it doesn't matter what the constant is. Well, it does matter, but we won't need to know it exactly for the purposes of this calculation. And so it's the probability of heads times to the power alpha minus 1, and the probability of tails to the power beta minus 1. There's probably some number between 0 and 1. So then the data are in Bernoulli trials, and the joint density is for those Bernoulli trials is p to the number of successes times 1 minus p to the number of failures. Again, something that we've seen in the past. And so the posterior distribution for the parameter p given the data x is just proportional to the likelihood function f of x given p times the prior. And the way things are set up, we have sort of a nice algebra. So I wrote down, first of all, the posterior distribution, which is a p to the number of successes times 1 minus p to the number of failures. And there's this constant times p to the alpha minus 1, 1 minus p to the beta minus 1. And you can collect all the powers of p and all the powers of 1 minus p. And you see, if you stare at the exponent for just a minute, that the exponent in front of p is alpha plus the number of successes. I'm sorry, the parameter is, the exponent is that minus 1. And the parameter in front of the 1 minus p is beta plus the number of failures. Okay, so using a beta 3 prior, we can look at credible intervals after, I'm going to show you two pictures, 6 successes in 10 trials and 16 successes in 25 trials. So if I want to do posterior, so the posterior distribution is going to be 6 successes in 10 trials, so I add, so that's 9 successes and 4 failures, so that'll be beta 9, 7. in the top case, and in the bottom case, it'll be beta 19 and then 9 failures, so 19, 12. So in the case of beta, in the case of 10 trials, then it's the posterior distribution is a beta distribution with parameters 9 and 7, and I used the round function because just to keep three decimal points, and so that's going to help you get credible intervals for the posterior distribution, right? So just to pick one out, the 95% credible interval will go from the 0.025 quantile to the 0.975 quantile. So it goes from 0.323 to 0.787. And just to have it in front of me, the width of that is 0.464. And then if I go up to 25 trials and I do the same computation, then the credible interval gets narrower. That should be the case. So rather than going from 0.323 to 0.787, it goes from 0.439 to 0.773. So that's a width of 0.334. So I'm gonna save that width of the other one. It's 554. Okay. If I did it right, 454. So there they are with the posterior densities, and I have a little red tick at the upper and lower confidence interval. So there's 2.5% of the probability below 0.323 and 2.5% of the probability above 0.787, and a similar statement for the lower posterior density. It's 0.439 for the lower density and 0.773, and there's 2.5% above that. One of the things that is typically pointed out, I meant to write this on the slides, for these credible intervals, it makes them a little bit nicer than for confidence intervals, is if you do, let's say, a confidence interval that's based upon the binomial distribution, then your distribution is discrete, and there's issues of what goes on at the boundary. That makes things complicated or sort of messy. And but it's something you have to live with if you want to work with confidence intervals that are on the boundary. On the other hand, if you have a continuous distribution as the prior on the parameter, and then you collect data, you typically have a continuous distribution on the posterior. And then since you have a continuous distribution, there isn't this problem of dealing with the tails of the distribution function and discrete random variables. So in some sense, that makes life a little bit simpler. Okay. Oh yeah, so there it is. Since the posterior distribution is a density, we don't face the same issues that were involved in finding confidence interval for discrete random variables. So I just explained that. I forgot that I wrote that down. And in choosing the narrowest interval, we follow a procedure similar to that used in minimizing the length of a confidence interval. So that means, this case, I'm going to do a 95% confidence interval. Again, my posterior density is a beta distribution. So I'm going to look at the gamma plus A confidence level and the A confidence level. And so there are two different quantiles, excuse me, that differ by 95%. And then I'm going to optimize that to pick the smallest choice. And when I do that, the minimum, it takes place at 0.028. So that's pretty close to the middle. So we're not going to get, the distribution is symmetric enough so that we're not going to get a whole lot narrower if we choose to take the highest density confidence interval over the equal tail confidence interval. And so the width is 463. That seems odd because that seems bigger than the width for the highest density one. 454. Why is it bigger? So I don't, anyway, and then so there's the upper level and the lower level. 463. So I'm not sure about why that's wider. Okay. If we do the same thing with normals, we've talked about the distribution of normal random variables In the past, if you have normal prior and normal observation, then you'll have a normal posterior. And it's nicer to do the formulas for the normal distribution if, rather than using the variance as the parameter for the model, we use 1 over lambda naught. So lambda naught is the information. And then the observations come from independent random variables, which are normal sigma. So sigma, the prior density is on sigma. So it has, and then its standard deviation, or its variance, excuse me, sigma squared. So we know the mean is normal with whatever the mean is for the normal distribution, and then sigma squared over n, right? And we've seen that many times before, that the sample mean of normal observations keeps the same mean, or any observation keeps the same mean, and then the standard deviation goes down by a factor of n. The variance goes down by a factor of n. So the posterior distribution we saw is some weighted average of 1 over lambda naught and x bar, and I'll write that weighted average down in just a minute, times sigma squared divided by n plus lambda naught sigma squared. So let's go. So the weighted average between theta 1, which is the middle of the prior distribution, and x bar, which is the middle of your data, the weights are lambda naught, which is the amount of information that is contained in the prior that goes with the prior mean, and then n over sigma squared, which is the amount of information that's contained in the data. And then in order to make probabilities, we take the sum of those two numbers and put them in the denominator, so it's a weighted average. So then the gamma level confident interval, credible interval, excuse me, is symmetric about that middle, and its width is some upper tail probability for the z distribution, 1 minus gamma over 2. And then it's multiplied by, rather than sigma naught, excuse me, sigma squared over n plus lambda naught sigma over n, it's got an additional term, lambda naught sigma squared, excuse me, in the denominator. And that extra term means that the credible interval will be narrower than the confidence interval, because we have used some information about what the middle of that data could look like and how spread out it is. So you get narrower intervals, typically for credible intervals and confidence intervals. And because the posterior distribution is normal, and normal densities are symmetric about the mean, then that credible interval is both equal-tailed and narrowest. Okay. So one approach to choosing a criterion is to adopt the idea of a loss function. And so the loss function takes two pieces. We're going to penalize ourselves from having an interval that's too wide, and we're going to penalize ourselves if we don't include theta in the interval. So those are the two penalties. And so the loss is the sum of those two things, right? You get an amount, a function of u of the length of the interval, and you get another loss of size c if the parameter is not in the interval. So that's the total loss. If you look in a variety of textbooks that I looked at yesterday, or different accounts, they write u of b minus a with, they write just the length of the interval plus some constant times the indicator of theta not being in the interval. And then they make the comment that that penalizes the situation when b minus a is big. So that has a tendency to weigh things on the second term. And so I mitigated that with using a function u of b minus a, which may, let's say, be sublinear, so that at some point you care less and less if the confidence interval gets larger. Having said all that, we have this usual sort of decision-making situation that we often see in Bayesian statistics. I couldn't find a single example where people use it. So in this case, the risk is the expected loss. So the expected loss is just the expectation of that term in the top. So the first term is just a constant, and the second term is just the probability that theta is not in the interval multiplied by c. And so now you choose you choose A and B to minimize the risk, given the data. So the credible interval chosen is the one that minimizes the risk. Okay, I promised you today's lecture would be shorter. So let me compare the approaches. This is the last slide today. So in Bayesian statistics, we begin with a prior probability on a parameter space. That's how we start in Bayesian statistics. And in classical statistics, we begin with a family of distributions indexed by that parameter. So we start with different places. We don't have any idea of what it means to be a prior distribution in the classical approach. We just know that we have a family of distributions. So, so use the data and Bayes formula to compute the posterior probability. That's what you do in the Bayesian approach. In the classical approach, you use a significance level to construct a random interval. And we've been writing that theta hat L for the lower end and theta hat U for the upper end. So now I have, I use Bayes formula, I compute a posterior probability. I use significance level, I construct an interval. Oh, well, somehow, so you get to see text colored teal, but so I'll fix that so it is really teal colored. So the credible interval has posterior probability gamma, that the probability with, and that is the probability that theta lands in the interval, lands in this interval. And the interval in this case is a random quantity. So you can say with confidence that that the interval is that gamma is the probability that your parameter is in that confidence interval, or in that credible interval, excuse me. On the other hand, the creation of the confidence interval, you should think of it as a single Bernoulli trial with success, with probability success gamma. So you can't talk about the probability that the parameter is in the interval, but you can talk about the chance that the interval captures the parameter. So that's the comparison between the two. I'll clean up this last slide for you and upload it in just a minute. So that's all I have to say today. Tuesday, we're going to go on to these new issues on chi-square distributions. So if no one has any questions, we have what I knew would be a sort of a shortish lecture today. So anything that you'd like to ask before we go away? I hope I recorded it. Okay, see you. I don't know that.